In this lecture, we are going to focus on counting. We are talking here about counting the number of outcomes, whether it is the number of outcomes in a sample space or the number of outcomes in a particular event. This is part of the material that you can find in the second chapter of, and the part that we are focusing on is particularly counting, as mentioned. We are gonna study efficient rules that enables us to do the counting in a very efficient manner. Particularly, we are gonna learn the multiplication rule, which has to do with counting the number of outcomes in an event or in a sample space when your random experiment is composed of multiple steps and there are a set of possible outcomes at each step, and then you are looking for the overall set of outcomes after doing the number of steps. We are also going to study the permutation rule, which is quite useful when you are dealing with a random experiment with, again, multiple stages or multiple steps, but then the ordering does matter when you are doing the representation of the outcomes. So whether, for example, you get a yes in the first trial and a no in the second trial, or a no in the second trial and a no in the first trial and a yes in the second trial, these are distinct for you, so ordering does matter. And the last is the combination rule, which is quite useful in counting the number of outcomes when you are doing experiments where ordering does not matter. Okay. So let's start by the multiplication rule. Assume that, again, if you remember the tree concept of constructing the number of outcomes in a sample space, assume that you have k steps. So you have a first step, first stage, a second stage, a third stage, for example, okay? And in the first stage, in the first step of the experiment, there are n1 possible outcomes. So the number of possible outcomes here is n1, right? And then for the second stage, okay, there are n2 possible outcomes. So for example, in the first stage you are flipping a coin. In the second stage you are rolling a dice. So the first stage of the experiment, the coin can produce 2 outcomes, so n1 is equal to 2. In the second stage, rolling a dice can produce 6 outcomes, so n2 is equal to 6, and so on. So here we have n2. So for each one of those there are n2, right? So n2, n2, all the way up to this one, which will also in the second stage will have n2, right? And then in the third stage, right, the trials are gonna have something like n3 number of possible outcomes. So if you perform the experiment, there are, for example, after rolling the dice, you are, for example, selecting randomly a ball out of a box where the color of the ball can be one of 3 different colors, right? So n3 in this case will have 3 possible outcomes, and so on, right? So for each one of those you will have the n3 and so on, right? So the tree build up, okay? Remember that we said that in this case, to count the total number of outcomes, you needed to count the leaves, right? And if you look at how these leaves, how the number of leaves is produced, it's basically for each branch here, for each of the n1 branches, there are n2 possibilities, right? So for this one there are n2, and for this one there are n2, and for this one there are n2, and so on. So up to this level it's n1 times n2. Then if you go to this third level, right, you have for each one of these, there are n3 possibilities. So the total number of possibilities is going to be n3 times n2 times n1, and so on. So if you have k steps, so k stages, right, and you have n1 in the first, n2 in the second, up to nk in the kth, then the total number of possible outcomes is going to be the multiplication of those outcomes at each stage. And that's called the multiplication rule. So this is the multiplication rule, and this is how you can relate that to a tree. Here is an example. Assume that you are designing a website And there are a few options that you can use. So there are different colors. There are 4 colors you can select as the background, for example. There are 3 possible fonts that you can use for the text in the web page, and there are 3 possible positions for the main image of the web page that you can use. So how many possible designs you have for this web design? The multiplication rule says that you have 3 steps of doing the experiment. You have to choose a color, and then after that you choose the font, and then after that you choose the position of the image. And the combinations of all possible choices, the total number of possible outcomes is equal to when you choose a color, you have 1 out of 4. So there are 4 possible choices here. When you choose a font, there are 3 possible fonts. And when you choose the image position, there are 3 possible positions. So N1 is equal to 4, N2 is equal to 3, and N3 is equal to 3. And the total possible number of outcomes is the multiplication of those N1 times N2 times N3. So you get a 36 possible designs. So for example, you select the color to be blue and the font to be Times New Roman and the left hand side position. And then there is another possibility, you select the color, for example, to be red. So assume that the colors are red, blue, black, and white, for example. And you can select the font to be Arial, and you can select the position of the image to be the right hand side or the left hand side, and so on. So if you combine all of these, you will find the total number of possibilities is equal to 36 as calculated here. Now let's look at a different situation where you have an experiment. You have a number of elements which is equal to n, right? And you want to get all the possible orders of these number of elements. So assume that you are choosing them one after the other in an ordered fashion, right? So how many possible outcomes you can have? For example, let's look at this case. If I have a set S which is composed of 3 possible letters A, B, and C, okay? How many possible ways I can put these 3 in different permutations, different orders, right? So I take the 3, all of them, and I figure out what are the number of possible reorderings that I can do. So there is an ABC, ACB, BAC, BCA, CAB, and CBA, right? So these are all the possible orders here. And if you want to count these are 6. And the way they are generated, if you want to know their number without constructing all the possible outcomes, in this case, the number of possible rearrangements of all these elements together is equal to the factorial of their number. So I have here 3, so it's equal to the factorial of 3. And the factorial of n is equal to n times n minus 1 times n minus 2 all the way to 1, right? And this is the way to do it in Excel, by the way, if you need. And by definition, the factorial of 0 is equal to 1. So basically, the permutation rule says that if I have a set of n elements, and I want to get all the possible, so the outcome of my experiment is that I'm looking for all the possible rearrangements of these elements, the ordered rearrangements of these elements, then in this case, the total number of outcomes, the total number of rearrangements in this case is equal to the factorial of the number of elements, so the factorial of n, okay? Now, can you deduce this from the multiplication rule? Try to think of a way that you can figure out where does this rule come from if you apply the multiplication rule. And so there are other ways to do permutation. So the previous slide was talking about a set of n elements, and then you are doing all the possible rearrangements of those n elements. Assume now that I have a set of n elements, but instead of doing the rearrangements of all the n elements together, assume, for example, that using the similar example that we had in the previous one, I have S which is equal to A, B, and C, and I'm trying to find all the possible outcomes where ordering does matter to me, where I am selecting only 2 out of these 3 elements. So the total number of elements is equal to 3, while I'm trying to choose only 2 out of these 3. So what are the possible ways? So I can choose AB or BA or AC or CA or BC or CB, right? So in this case, I'm trying to choose 2 out of 3 elements, and then I'm looking at all the possible selections with ordering as part of my distinction between one outcome and the other. And in this case, the total number of possible outcomes here, which is in this case, for example, comes to be 6 possible outcomes, can be calculated using the permutation calculation. So n, the number of elements, r, the number of choices that you are trying to choose, and in this example, n is equal to 3, r is equal to 2, so you have 3p2, which is equal to the permutation of the permutation of 3 2 times is equal to the factorial of n divided by the factorial of n minus r. So in this case, it's the factorial of 3 divided by the factorial of 3 minus 2, right? Which is going to be equal to 3 times 2 times 1 divided by the factorial of 1, which is 1. So this is going to be equal to 6 as shown here. 6 possible outcomes, right? And the permutation in Excel can be performed using this operation. Again, try to think of how you can deduce this rule from the permutation rule that we studied in the previous slide, combined with the multiplication rule, taking into account that what you are doing here is trying to choose r out of n. So you are not taking all the n elements together, you are only taking a subset of the elements. Okay. The next slide here shows us an example, which is a kind of a nice example to have a look at, that illustrates the permutation. So the example says that assume that you have a printed circuit board, right? And this board has 8 possible locations for placing the components on the board. Okay. So 8, those red boxes are 8 possible locations for the printed circuit board. And I have 4 different components. So assume that my components are represented by those symbols. So this is one component, this is another component, this is a third component, and this is a fourth component, right? So I have 4 different types of components, okay? And they are different components. So I have 4 that are different from each other. Each one is a different component. How many ways I can place those 4 different components on the 8 possible locations of this printed circuit board, right? Now if you think of this problem, placing the circle, for example, here, and the triangle here, and the hexagon, for example, here, right, and the star here, right, is different from, again, occupying those 4 places, but with different arrangements. So for example, I can decide to do this, right? Put the hexagon here, right? And the circle here, and the triangle here, and the star here. This blue arrangement is different from the black arrangement that we see, even though I've placed all the 4 components in exactly the same 4 places on the printed circuit board. In addition, if I place the if I choose other locations, that's also a different. So if you think of this, it's as if you are trying to pick those locations, right? Those locations on the printed circuit board. You are trying to pick 4 out of the 8 because you are placing only 4 components. 4 out of the 8, and ordering does matter in this case. So if you put the circle here and the hexagon here, so if you put the hexagon here and the circle here, it's different from putting the hexagon here and the circle here. These two arrangements are different because you care about ordering, right? So it is as if you are choosing 4 out of 8, right, with ordering, and in this case the total number of possibilities is equal to the permutation of 8 4 times, right, which is equal to 8 times 7 times 6 times 5, or the factorial of 8 divided by the factorial of 4, which is equal to 1680 different placements or layouts or designs. Okay. Another different type of permutation is the case, so the previous case was choosing r different elements out of n elements with ordering. In this case, in this slide, we are looking at the case of subsets of similar objects. So assume, for example, that I have a set of n objects, right, which are composed of n1 similar to each other, n2 similar to each other, up to nr. Right, so let's say if I want to do an example for this, I would say that I have the following 8 elements, for example: a square, a triangle, a triangle, a triangle, and a circle, a circle, a circle. So this is n1, this is n2, this is n3. How many elements I have? 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 elements. So n is equal to 8. n1 is equal to 3. n2 is equal to 3. n3 is equal to 2, right? And these are similar, these are similar, these are similar. So these are subsets, but the total number of elements is equal to n. Now, if I want to do reordering of these and figure out how many possible outcomes are gonna come out of this reordering, right? Notice that if I do this, for example, this, a triangle, and then a circle, a triangle, a square, right? Now, it doesn't matter if I switch those two, right? Because they look similar. So switching here would not matter. Or if I switch those two, right? Doesn't matter. Or if I switch this triangle with this triangle, right? Doesn't matter because they are triangles. So moving them around is not going to change the outcome, right? So now I want to know how many possible outcomes I have in this case, and the rule of permutations of similar objects says that this is equal to the factorial of the total number of elements, which is n, divided by the factorial of n1, the number of similar elements in group 1, divided by the factorial of n2, the number of similar objects in group 2, divided by the factorial of n3, the number of similar objects in group n3, and so on, assuming that I have r similar groups, okay, or r type of groups. Okay. Now again, can you think where does this rule come from and deduce it from the previously studied permutation, which is the factorial of n, and the multiplication rule? Again, those questions that I have there are for you to think of, but they are not kind of like requiring a formal proof, or it's just for you to try to deeply understand what's happening and figure out where do these rules come from, such that they make sense to you. Okay. Here is an example on the case of the subsets of similar objects. For example, assume that I have in a hospital an operating room which needs to schedule 3 surgeries on the knee, so 3 knee surgeries, 2 hip surgeries, right, in a certain day. Okay, so assume that we say that a knee surgery is denoted as K and the hip surgery is given the symbol H. How many sequences are there? Again, we have here how many possible outcomes? We have 3 plus 2, so we have a total of n equals 5. How many groups? We have 2 groups. This is a group of similar outcomes, and this is a group of similar outcomes, right? There are 2 groups of similar outcomes, this one and this one. In the first group, n1 is equal to 3, right? So there are 3 elements, 3 operations. And in the second group, n2 is equal to 2, right? And the sum of those gives you the total number of possible outcomes, right? Okay. 5 operations in a day. Okay. Now, how many possible ways? Again, it's simply the rule says n divided by factorial of n divided by the factorial of n1 times the factorial of n2, which is what you see here. And then if you expand those factorials, you should get a total number of 10. And here it shows you those possible outcomes. So ni, HH, KKH, KH, and so on, right? This just lists the possible outcomes. You can do them exhaustively as shown here. The last way, or the last method of counting, is called the combinations method. And this is very similar to the permutations method, the first permutation method, where here we have a set of n elements. We are trying to choose out of them r elements, but in this case those r elements are similar, so they doesn't matter the order of those r elements. So if I have to choose r elements out of n elements, where in the choice the ordering of the choice does not matter to me, right? In this case, the way to calculate this is by doing the combination calculation. R out of n, which is equal to the factorial of n divided by the factorial of n minus r. This is exactly npr, right? These two combines as npr, and then this is divided by the factorial of r. So you can say that cnr is equal to pnr divided by the factorial of r, which is equal to the expression that you see, right? This is called the combination. In this case, you can explain this by saying that I want to count the number of subsets. So I have a set of, for example, S is equal to A, B, C, and I want to choose 2 out of 3 out of these 3 elements. So R is equal to 2, N is equal to 3, as we see here, right? I want to choose 2 subsets. And don't forget that in sets, the ordering does not matter. So the possible subsets are A and B, and it doesn't matter which one comes first. The other subset is A and C, and it doesn't matter which one comes first. And the last subset is B and C, and it doesn't matter which one comes first. So there are only 3 possibilities, which is equal, if you want to calculate, the factorial of 3 divided by 3 minus 2 n minus r factorial, right, times factorial r. Factorial r in this case is 2, and this is equal to 6 if you calculate, right? So here is an example which is very similar to the previous example. So we have a printed circuit board that has 8 possible locations, right? And I want to place 5 components, right? But those components are identical. So for example, all the components are stars. So 1, 2, 3, 4, 5, right? In this case, placing this guy here and this guy here is very similar to placing this guy here and this guy here. As long as I occupy exactly the same locations, it doesn't matter. So in this case, it only depends on which locations I'm picking, right? Doesn't matter which component is put, because the components are similar. And in this case, it's as if I'm choosing R equal to 5 out of N equals to 8 without caring about ordering, right? So choosing 5 out of 8 without ordering, and the total number of calculations is going to be C85, which is equal to the factorial of 8 divided by factorial of 5 times factorial of 3, which is equal to 56, right? That's the example of. Last thing is the concept of sampling with or without ordering, with or without replacement, sorry. And this is again a very important concept. For example, assume that, just to illustrate the concept, and then we'll see examples when we do the exercises in the exercise sessions, right? So assume, for example, that I have the letters A, B, C, and D put in a particular bin, and I'm trying to figure out what are the possible outcomes if I choose 3 out of those 4 letters. But when I'm doing the choices, I'm not placing back my choice into the bin. So the first choice I'm gonna do is gonna pick either an A or a B or a C or a D, because 4 of them are inside the bin. Now assume, for example, that in the first case I chose B. Now B is outside the bin, and I'm gonna do a second choice. The second choice will have only C, A, and D remaining, right? So for the second choice, I will have only 3 possibilities. Now after taking one of these, let's say the A outside, for my third choice, I'm gonna have only 2 possibilities, the C and the D, right? And so on, right? What if I'm doing the experiment? This is called without replacement. So this is without replacement. What if I'm doing the experiment differently? So I have the A, the B, C, and D. And then what I'm doing is choosing the first guy, A, right? And then putting it back in. Now when I'm doing the second choice, how many possibilities I have? The A is back. So I do have the A, B, C, and D. All the four are again available. And then I'm doing my second choice. Let's say my second choice was a B. And then I put it back in. Now I have to choose for the third time. How many possible outcomes are there? Again, since I put the B back, I still have the four of them inside the bin. I'm doing my third choice. Okay? And this is with replacement. Okay? Now the outcomes, the possible outcomes in the two different cases is going to be different, as you can imagine, and we'll see that in some of the examples.